that, I'm sure our next speaker has a lot to say about this challenge between AI and humans. We have seen recent success of reinforcement learning in many, many different gaming kind of constructs, starting from Go, where they beat the world champion, and recently they're doing very well in StarCraft and open systems like Dota. Peter Wurman is the director of Sony AI, and his team and his collaborators recently programmed AI called Sophie in a racing game, in a very high fidelity photorealistic racing game, where they were able to match and surpass esport racing driver performance. And so with that, I invite Peter to share with us this remarkable journey and achievements. And if you haven't done this already, Peter and his team, they published this work in Nature a few months ago. This is sort of the only work I know of where racing has appeared at the topmost journal, very respected as well. So great accomplishment, Peter. Looking forward to hearing all about this. Let me pull up your slides.
Okay, well, thank you very much for the chance to talk about our project. I'm P. Wurman. I'm the director of Sony AI America, and I was the project lead for the Gran Turismo project. Oops, arrow keys won't work. Okay. Sony AI is a relatively new organization, was founded in April of 2020. I run a remote workforce. We're spread all over North America. There's offices also in Tokyo and Zurich. You can learn more about it on our website. I also run the Game AI project within, it's one of our 3 flagship projects within Sony AI. And that's what I'll talk about today. This was a partnership between 3 different groups within Sony. Sony AI, as I said. We also worked very closely with Polyphony Digital, who makes the game Gran Turismo, and Sony Interactive Entertainment, which does a lot of things, including builds the PlayStation. But the group we worked with runs PlayStation and the cloud service that you can use to play PlayStation games remotely. When you're not using it, we get to use it for training agents. Gran Turismo, you may have heard of. It's a very high fidelity simulator. There's still obviously a huge gap between simulation like Gran Turismo and racing in the real world, but there is a lot of real physical effects that are modeled within the game, including slipstream effects, tire slip, the impacts of aerodynamics and downforce and traction, and a lot more. There's a very robust esports community around the game, and it's been used by professional drivers for training and was recently featured in the Virtual Olympics, which was the first time virtual events were held in conjunction with the Olympics. I don't know what's going to happen here, but click. This way. So our grand challenge was to train an agent that could race with the best humans of the world at this game. And we wanted to be able to do the kinds of things you see here in this little clip from the 2019 World Championship. Nice, clean racing. I let it run a little second longer because the person in this car's name is Tamaoki Yamanaka. He was the winner or on the winning team of this particular race. He's one of the human racers that we're going to race against. So what we did was set out to win 3 race series on 3 different tracks within the game. They're all pretty popular and complex tracks, each with 3 different cars. First one is called Dragon Trail Seaside configuration. Lago Maggiore was second, and the last one was Cirque de la Sarthe, which is, of course, a 24-hour Le Mans track. And each was a progressively more difficult, more realistic racing car. And the 4 human drivers are on the bottom there. Takuma Miyazono is on the left side. He was a 3-time world champion in 2020. Yamanaka second, and 2 other top drivers from Japan were also in the race. We used end-to-end reinforcement learning, which you heard a little bit about earlier today. Basically, the agent is set in the world. It runs on a separate computer from the game. It's set into the environment. It learns by trial and error how to drive and eventually how to race. It observes the state of the game, and it gets rewards that we program into the agent. And through that experience, collecting lots and lots of experience, it learns to drive. We broke it down, I think, Johannes, you said there were 3 ways to break down racing. We broke it down 3 different ways. The first major category we thought of was race car control. The agent had to be really good at operating the car at the edge of its traction limits. The second was to try to encapsulate racing tactics so that it knew how to pass, when to pass, hopefully it could learn blocking and other maneuvers, use the slipstream effectively, and those kinds of things that you see real racers do. And finally, one of the hardest things was that we wanted it also to respect the racing etiquette of the game and of real racing. And I'll come back to that in a little bit more detail, but that is a hard problem. So let me talk about, I'm going to keep this very high level. There's way more information in the paper. I'm happy to talk about later, but I'll just try to get across the high level points in this short talk. So first, the car has just actions in 2 dimensions. It can throttle or brake, and it can turn left or right. It gets a variety of rewards for the time trial aspect of this. Its main reward was progress along the course. Its position mapped to the center line, and the distance it went from time step to time step was the reward. And it gets penalties for tires slipping, for having more than 2 tires outside the course boundaries, or for hitting a wall. It knows, what does it know about the world? It knows, of course, its own XYZ velocities, its accelerations, and its angular accelerations. It knows the loads on each tire and the angles that they may be pointing relative to the car's direction of travel. It also has the actual position it is along the track, but just as important is it has a 6-second perspective of the course in front of it. So based on its current velocity, we calculate points along the edges and along the center line for 6 seconds, assuming no velocity changes. And that information is fed into the neural networks. You can see as it comes around this corner on the bottom that because it's slowing down, that window in terms of distance compresses, but in terms of time, it's still approximately 6 seconds. We used soft actor critic methods to train the agent. We had to enhance them a little bit with what we call a quantile regression soft actor critic algorithm, which learns not just an estimate of the mean future value, the Q function, but it learns a distribution of that Q function over time. We also found that it performed better when we used n-step returns instead of, there we go, the simple one reward plus estimated Q function. If we use the rewards for several steps ahead, that performed better. So QR-SAC allowed us to shave off about 0.6 of a second from SAC alone. And the n-step rewards, if we had just used n equals 1 versus what we used in the final event, n equals 7, that was another, that also added about 1.5 seconds. This is what the race car control looks like. This is a time trial setting, and it's coming through a corner on Dragon Trail C side towards the bottom right of the corner, and entering a chicane known as the chicane of death, because as you'll see how tight the walls are as you drive through this section, and you have these curbs and stuff, and you'll see how close it comes to the walls here, and it just barely learns to control the car at very high speed through that very tight series of corners. But of course, being fast isn't enough. What really matters is that you've learned to race, and therefore you need to know about the other cars on the track. We encoded those to the neural network by using 2 lists. One, a list of the cars in front of the agent, ordered from closest to farthest away up to a certain window of distance. And one, the cars behind, again, from closest to farthest away. And the agent had access to the position and velocity of those cars and their acceleration relative to itself. And some of this information you will say, well, this is a little bit more precise, more accurate information that the humans had. That's true. In general, I answer that question by saying The information it generally had in a more precise format, but it also had less information overall. For instance, in this case, it sees all the other cars only as the points, the center of mass of those cars. It doesn't know the dimensions of those cars. Fortunately, it's in a race where all the cars are the same size, so it's able to generalize that information from the way it may learn where it hits them. To encourage actually winning the race, we also added a passing reward. And this was a symmetric reward term that was added that we used to encourage you to catch up to and pass other cars. And so within the difference of 2 time frames, if you closed the gap with another car or increased your lead on another car, you got a small reward for that. If the other opponents did the same to you, then you would get a penalty for that, for them catching up to you. And that was applied to all cars in your vicinity. Now we get to racing etiquette. So if you're familiar with racing, this is the most imprecise part of the sport. This is a little block of text taken from the FIA guidelines. And I highlighted in green the terms that are particularly subjective about these definitions. You can get a penalty if you cause an avoidable collision, if you illegitimately prevented a pass and overtaking maneuver. And these things, as you know, are evaluated by human judges kind of in real time with a bit of a delay. They look at what happened. They actually may take into consideration the context and the outcome of the incident when deciding whether you get a penalty. So if you have a little bump, but nothing bad happens and there's no change of positions, you may not get a penalty. That same bump, but if it causes your opponent to spin out or go off the course, you may get a significant penalty. So we tried to capture that as best we could. In the end, we used these reward terms to encourage good sportsmanship. Basically, the agent got a penalty for any collision it was involved in, whether it was its fault or not. It got an extra penalty if we think it hit the other car in the rear end or somewhere in the back end, and we considered that the agent's fault. For Sarth, where we were using the Red Bull competition car, which was particularly fast, and it's a very complex technical course, we had to add a few more penalty terms to try to capture, to encourage good behavior in that setting. So side swipes on straightaways were penalized. There was an additional penalty for rear ends on straightaways. And any collision in a corner, if the opponent wasn't bumping you from behind, was penalized. Okay, so that's kind of the structure of the reward setting and the features that were available to the agent. Then we had to try to teach the agent to actually race. And this being reinforcement learning, of course, what we did was we created scenarios where it could gather a lot of information about the environment and racing situations and try to learn from that. So down here on the bottom are, for the Sarth circuit, are some of the configurations that we put the agent into to try to gather a wide variety of experiences. On the left, we have kind of the standard, what we call the time trial configuration, which was training occurred with 20 cars equally spread around the track. Once you learn to drive around the track, they're all running the same policy, so they don't really interact with each other. Can I use this? I can. We also set it up in small pairs where there was one agent and one opponent of some kind, or in 1v2 scenarios, 1v3 scenarios where there's one agent and 3 opponents. And each of these were randomized with initial speeds and initial relative positions of all the cars. And then finally, because we could run up to 20 cars in one, simulation. Oh, how am I going to go backwards? Good. We could run up to 1v7 scenarios, but only 2 of those spread around the track. But we also found that we had to there was this kind of exposure problem where a lot of really important events don't happen naturally in these default settings. So no matter what we did, no matter how many 1v3 or 1v7 scenarios we ran, we didn't experience the kind of congestion you found at the start. So we had to configure another set of scenarios that would run periodically, pretty frequently, where we practiced the start of the race again. Also, slipstream opportunities just don't happen that often in a race once you become pretty good at it. So we set up scenarios where we got to practice exactly passing using the slipstream. And then finally, in this track, there's a very hard chicane at the very end that's very easy. It's 2 chicanes right in a row. It's very easy to cut the corner. And even if you penalize going off track, you save so much time. The agent is very much encouraged to do that. So we had to set up a lot of training around that. We actually added some special penalties to encourage you to stay on the track. We also found that the opponents that you trained against were very important. And so you had to train against opponents that were equally skilled, but also provided you with a variety of experiences. In the end, we used both the built-in AI, which was relatively slow but fairly courteous, and some line following Ph.D.-based agents that were really good on the straightaways, but we didn't use them in other places. And then we curated policies, different versions of Gran Turismo Sophie that we had selected for their good behavior. What we found, one of the effects that we found was this was really important in terms of etiquette. If we trained only against relatively easy agents to beat, like the built-in AI, then our agent became overly aggressive. And when we trained against agents that were that we had selected because they were aggressive themselves, then our agent became overly cautious. And this graph is the team score versus a good instance of Gran Turismo Sophie versus the number of collisions that occurred that could have been considered questionable and for which an agent could have got a penalty. So ideally, you'd like to be low and to the right, like the blue dots, which are the baseline agent that we ended up using. We also found that convergence in reinforcement learning, it's not defined as we converge to some specific world best optimal policy. Instead, it kind of oscillates around some range of behavior. And in this very complex situation where we are training an agent that's supposed to retain a lot of skills related to a lot of situations, we found that the performance around those skills would vary over time as the policy trained. So we ended up developing a very complex process for trying to find the best policies that we had trained, selecting them for races against humans. And it involved running several training scenarios in parallel, filtering out the best policies from there, running them against a larger fixed set of tests, again, filtering that set out. And then we ran them against each other in 4x4 player versus player scenario or agent versus agent scenario. We then ranked those. But really, to find out if they were going to be good in a race against humans, we had to race them against some test drivers. And even though things looked good when tested against other agents, sometimes those policies would get rejected by the test drivers because they were too aggressive or they displayed a weakness that we didn't uncover in our own testing. And that process allowed us to pick one agent that we could then run in a race. So we actually ran 2 races. The first was July 2nd. Like any event, we were pushing right up to the deadline to try to make it work. We did reasonably well. So GT Sophie won 2 of the 3 races, but lost the overall team score. So it was close, but we weren't able to win. We learned a lot from that experience though. And we came back in October, having improved the opponent representation, improved the neural network size, made some other fixes, figured out where our training coverage was incomplete. And in that race against those 4 top human drivers, we placed 1st, 2nd, 4th, and 5th in 2 of the races, 1st, 2nd, 6th, and 7th in the other race. And as you can see, the total team scores for the 4 races, the GT Sophie doubled the human score. And I'd like to leave you with a video, if I can turn it on. This is a little stretch where one of the GT Sophie agents in the gray car is racing head-to-head against Yamanaka over in Lago Maggiore. And this is, a head-to-head, wheel-to-wheel combat, just like you saw in that first video, but over, about 3/4 of the track. And that's exactly the kind of behavior we wanted to see out of this agent. And that's the kind of experience that these top drivers can't get anywhere else except by racing against each other. Yeah, so if you'd like to read more about it, we published an article in the journal Nature. I'm the first author, but there were 26 other people. Most of them did all the work, but I helped tell the story. And so you can read about that. And I'm happy to take questions afterwards. Thank you.